me start the recording here. Okay, so we learned in our last class about inverses of matrices. What is an inverse of a matrix? Well, if you have a square matrix A and you take A times its inverse, what will that equal? If A to the, it's denoted A to the negative first power, but this means the inverse of A right here. What is A times A inverse equal to? Good, that's right, Benjamin, that's right, Hung. The identity matrix. And then, of course, if you have A inverse times A, that also equals the identity matrix. And so you learn how to find identity, how to find inverse. Well, matrix A doesn't always have an inverse, but if it does have an inverse, you learned how to find inverses of 2x2 matrices, and then 3x3 matrices and higher dimension. There's an algorithm that you learned about in section 2.2. Sometimes, though, you want to use a computer to help you find the inverse of a matrix. And in this problem, dealing with what's called a flexibility matrix, we'll use MATLAB to find the inverse. So let me give you a moment to copy this example down. Let me just give you a moment here. Okay, so I know you're copying here, and I'll just make a few comments here. So this matrix D is called a flexibility matrix. And there's an example 3 in the textbook that talks about, gives a little detail about what the matrix D is. But in this example, you have a beam here, and the beam has 4 points on it where force is applied. Think of it like, 4 cars on a bridge, something like that. Okay, and the first column of the matrix D is the beam deflections due to a unit force at the first point. The second column stands for the beam deflections due to a unit force at the second point. Okay. All right. So when, like, for instance, if you have well, I'll make a comment here, actually, something very interesting. Let's focus on the on this first column here. Okay, so the first column is the beam deflections due to a unit force at point 1 right here. So if you have a material, you have a beam made of some material, and you apply a force at that point right there. Okay, on the left point on the beam. Where would of the 4 of the, you got the 1, 2, 3, 4 points here. Of the 4 points on the beam, if you apply a force here at the first point, which of the 4 points would have the greatest beam deflection due to that force? Which should have the greatest beam deflection? This isn't really, you don't have to take really physics to answer this. This is just sort of a use your intuition. Where would the beam bend the most? Yeah, that's right, Benjamin. The first point right there. When you apply a force at point 1, there will be deflections on all 4 points of the beam, but the greatest deflection should be right there at the first point. And if you look at the first column, okay, which value is the largest? It's the first value. It's the first value. Okay, which makes sense. And then the value here, why is this value here so low? This last value, 0.0005. That's a lot. That's 8 times less than 0.004. Why is this value here like greatly reduced from the first value here? What do you think that is? The values in the first column here seem to be decreasing. Why is this force value? That's right, Benjamin. The fourth value is the 0.0005 is the beam deflection due to unit force at point 1. Well, the 0.4 is furthest away from point 1. So it makes sense that the deflection at point 4 is going to be very small when a force is applied to point 1. Okay. Similarly, let's go to the last column here. the last column. So that column stands for the beam deflections due to a unit force at point 4. Okay, so at point 4, it says, well, there's a force applied, some force, F4, applied at point 4 on the beam. Well, which deflection is the smallest? At point 1, point 2, point 3, or point 4? Looking at that column, which deflection is smallest? That's right, Defani, point 1. Why would that make sense? Why would that make sense? That's right, Defani. Point one is farthest away from where the force is applied at point 4. Okay, the F sub 4 force is applied at point 4, but point 1 is furthest away. So the beam deflection due to a unit force would be smallest at point 1. Okay. All right. So does this? So sometimes I think this is a really nice example because it shows you that these numbers in the matrices, they have meaning. They have meaning, and you've seen that before, but it's always nice to see a new example. Now remember the units for these numbers in matrix D are in centimeters per Newton of force. And they're saying that measurements of the 4 points show deflections of 0.08 centimeters, 0.12 centimeters, 0.16 centimeters, and 0.12 centimeters. Okay, determine the forces at the 4 points. Okay, determine the forces at the 4 points. So the idea, well, yeah. So, all right, I'm going to show you how to solve this problem. Are we ready to move to the next page? All right. Well, so really this problem, using the units, is helpful in understanding, in a sense, how to solve the problem. Because I'm going to go to the next page. And what I've done is I've written out the matrix D here. But for every element in the matrix D, I've put the units there. Not just the number, but the units. So, and the vector F is the force vector. That's our vector of forces. That's what we're looking for. And the vector Y is our vector of deflections. Does it make sense that if you take the deflection matrix, D, and multiply it by the force vector F, that will give you the deflection vector? Does that make sense based on the units that you see in the matrix D and the vectors F and Y? Okay, good, Nafani. Good. I mean, think about it for a moment. If you take, like, you know how to do matrix multiplication now very well. If you were to do matrix multiplication, okay, say, to get the 0.08 centimeters, you'd have to take the first row and in the matrix D and multiply it by this column here. The column, the vector F. Well, what when you multiply, when you do the matrix multiplication, what's gonna simplify out in your matrix multiplication? You know, what units would you be left with when I'm talking about the row column rule for multiplying matrix D times vector F. Yeah, that's right, Nafani. Centimeters are going to be left because every multiplication you're taking a number whose units are centimeters per 1 Newton and multiplying it by a force in newtons, and so you're left with centimeters. Okay, so this makes perfect sense. How many find writing the matrix with the units there to be helpful in understanding this matrix equation? How many of you find that helpful? Good. Andres does. Good. Natalie, excellent, excellent. Excellent, Abby. Wonderful. Samantha, excellent. Good, marvelous. Good. And of course, in the homework for this kind of problem, they don't put in the units. They have a word problem like the one you copied, but to help you understand the problem, and it helps to put in the units. And they don't tell you to do that, right? They don't, like when you work the problem out, you just you might go through the motions and so forth and work it out, but you can put the units in like I did to help you understand what's going on. There's nothing wrong with that. And it isn't like anybody's telling you to put the units in on all these numbers here, but you can do that. It's a free country, and by doing that, it helps. So we want to find now the force vector F. Since D times F equals Y, okay, and D, of course, D is a square matrix. I mean, let's always remember when we talk about, inverses, we need to have a square matrix. Well, if D times F equals Y, then F will equal D inverse times Y, right? And you're going to get then the forces on points 1, 2, 3, and 4 of that beam. Okay, are there any questions on that? D inverse, by the way, is what's called your stiffness matrix. It's called the stiffness matrix. And how do you get the inverse in MATLAB? There's a command called INV. So in MATLAB, all you have to do is you type the matrix D in, okay, you type the vector Y in, and you go D inverse times Y. But how do you get this? How do you get this inverse matrix in MATLAB? You wouldn't want to work this out by hand. Now, of course, in the homework, you do have a few problems where I want you to work the inverse out by hand, like two by two. There's a square matrix. There's a formula for the inverse. A 3 by 3 matrix. There's an algorithm. And even a 4 by 4 matrix, if it's simple enough, you can work through the algorithm. But this matrix here, this matrix D here, you would use MATLAB to do that. And the command is called INV parentheses the matrix. INV is the command. Okay. So I think this is a really, let me just see here. All right, let me give you a moment to copy, to catch up here. One moment. So I think this is a really cool application. One thing I could think about is, for instance, if you, let me just see here, one moment, class. Yeah, so if you have a beam, or, well, let's talk about a beam, and it's made of a certain material, and, based on materials, uh, how many have seen like deflections in another course? Maybe another course. Has anybody dealt with deflections in like civil engineering? Maybe another course they've had, or okay, Marvelous has. Okay, so again, mathematical statistics is my area of expertise, but I can I mean, it's reasonable that different materials, beams made of different materials, are going to have different deflection constants based on the material. And if you have those deflection values in a matrix D, then you might say, well, okay, what if I wanted to apply a certain force, different forces at 4 points on the beam? What would my deflections be? And deflections are important because if the deflection's too much, what would happen to the beam if the deflection were too much at one point on the beam? What could happen to the beam? If the beam bends too much in one spot, that's right, Andres, it could snap. That's right. So this is really, I think, a very nice application. How many kind of think it's pretty cool? Seeing this application. Yeah, Lewis likes it, and Nafani, great, great. Catherine, wonderful, wonderful. All right, well, are there any questions? Are there any questions at all? Benjamin's comfortable, all right. Okay, well, let me stop the recording.